Hey everybody, welcome to today's webinar, Planning a Rendezvous and Proximity Operation Mission using Astrogator Sequences. Today we have Doug Cather, who is a technical director at AGI. Doug has been flying satellites for over 37 years, not just flying them, but he's been in all phases of the program life cycles, from the beginning, the concept, design and creation, all the way through test, all the way through operations. He's done it all. So Doug, welcome, and thanks for joining us here today.
Hey, Josh, thanks for that. I appreciate it. So today, as you heard, the discussion is going to be a quick overview of planning a rendezvous and proximity operations mission using some specialized Astrogator sequences. These sequences are not built in to the default Astrogator, but they have been built and are available to our customers on request. So anyhow, let's get started. So planning a rendezvous and proximity operations mission to date has had many different issues. Many of the current tools out there are quite time consuming and challenging. And in my experience have taken, sometimes days, weeks to plan a relatively simple mission. They typically require strong astrodynamic skills, an understanding of numerical issues. Frequently, additional scripting is required, and quite a lot of experience with your unique tool. So, in addition, understanding your specialized mission constraints, such as lighting issues and attitude issues, and those types of constraints are a real problem. So, anyhow, some of the common RPO tool limitations are many are done using the Clohessy-Wilshire equations. So they use a simple two-body propagation, thus not allowing any differential forces between your target and chase vehicles. They're typically used for circular orbits and close proximity only, because those assumptions start to break down. Many times, forced motion waypoint navigation is the only option. You just have to move, and as I call it, a hop from one point to the next. That can be very time consuming. Every one of those maneuvers then has to be verified to be passive safe, for example, and that type of mission planning is frequently just very time consuming. Many of these tools also allow for impulsive maneuvers only. None of these constraints exist inside Astrogator. We can perform proximity operations against a highly eccentric orbit, or in the presence of large differential forces. So maybe you're tasked with going and inspecting a large geosynchronous satellite because after launch there was some flaw and we just need to go observe it, or you're going over there to refuel it, for example. Well, there's a lot of differential force between a small inspector satellite and the large geo satellite due to the delta solar radiation pressure. So these constraints can all be handled in these sequences I'm about to present. So Astrogator is the key enabling software for this RPO mission. It's a specialized analysis module that exists in STK. It supports an unlimited series of events and modeling, and offers tremendous flexibility through the use of customized force models and engines and the likes. So all of this planning can be done using full finite, even including a relatively low thrust type RPO mission. So let's take a look a little deeper then into these RPO sequences that we've built inside Astrogator for use in the RPO mission. So first, a quick discussion. What are relative orbits? Relative orbits, in my opinion, come in two flavors. There's natural motion, and then there's forced motion. Natural motion meaning if your force models are matched, your solar radiation pressure and or drag models are essentially consistent, and you're operating relatively close between the chase and the target vehicle, then Then natural motion is supported for sitting on the V-bar or in the in-track direction. In the in-track direction, it's a stable offset. So you could sit there as long as the target satellite did not maneuver for quite some period of time before you'd have to do any sort of maintenance on your orbit to keep that same relative position. The same is true of a natural motion circumnav, which is a 2-to-1 ellipse around the target, as you can see in the picture in the lower left corner. Spiral flybys is another version of the natural motion circumnav, only it's drifting at the same time as it's doing this 2-to-1 ellipse. So it has a slightly different period and is just drifting past the target. A very interesting orbit, allowing you to inspect your target more or less passively from all faces as you go by, depending on how fast you want to drift by your target. The forced motion means it requires maneuvers, delta V's, to achieve these relative orbits. Some simple examples, the teardrop, as shown on the bottom center there underneath this column. You can see a teardrop orbit just requires a radial maneuver every time it hits the bottom of that teardrop, and it will naturally drift up and around and back down to the same point as long as you keep performing that same relative maneuver. Force motion circumnav is where we keep a perfect circle, not a 2-to-1 ellipse. That is not natural and requires maneuvers to keep it along that line. A perch point, one that isn't on the in-track direction or on the V-bar, will also require frequent maneuvers to keep it at that point relative to the target. Say you wanted to just persist in the radial direction from the target. That will take some maneuvers to keep it from drifting away. You might want one that follows the sun. And in that case, I mean, put your satellite between your target and the sun. That gives you really good lighting on the target. It's well lit up and allows you to do a really good inspection. But following that line, again, is not a natural motion and requires maneuvers to stay on that line. A hop is simply going from one point to another, or a waypoint can be implemented such that you follow straight lines between in a hop. You're going from one point to another, but you wish to do so in a controlled fashion rather than just letting it get there in a hop fashion. So let's look a little further. RPO missions have basic timelines. First, you rendezvous into the proximity of a target satellite. So this is the rendezvous phase. Then you might want to move closer in a passively safe mode. So you may want to, like, for example, V-bar hop along the V-bar closer to your target, because your initial rendezvous, you may not be so daring as to just try to get super close. You may want to rendezvous onto the V-bar, perform an orbit determination update, sit there for a bit, and then move in closer. Next step might be begin a desired relative orbit to meet your inspection requirements. So now you're in there and you need to inspect certain faces or whatever your mission may require. We then need to exit the scene, so moving in a passively safe fashion to a relative point, and then beginning an exit strategy to leave the scene of the target in a nice, safe fashion so that no one is at risk there. So Astrogator sequences for RPO. RPO missions generally have a limited set of building blocks. As I mentioned in that picture 2 charts ago, we looked at various different types. So we can build up a set of sequences that models each one of these types of RPO proximity type operations uniquely. So from the perch, the teardrop, the natural motion circumnav, we can build up a set of sequences for each one and then be able to use them to build up an entire mission. These can be captured in an Astrogator sequence, and we make full use in these sequences of the built-in scripting tool that exists in Astrogator to expose to you the parameters, the defining parameters of those types of sequence. We'll take a look at that in just a minute. The user doesn't need to really know the details of what goes on in the inner part of those sequences, but only the basic design parameters. Let's look at that a little closer. Here is a scenario, an RPO template, if you will. And what it does is builds up a mission from the RPO satellite relative to the target. So, for example, in this one, you can see we go through and we're going to rendezvous, we're going to hop, perform a circumnav, then we're going to hop to a inspection point where we're going to perch, and then we're going to coast and leave the scene. Let's take a look a little closer at one of that V-bar hop sequence that was in there. In the V-bar hop sequence, we've exposed a few of the defining parameters associated with a V-bar hop. The sequence knows when it gets to here where it is on the V-bar, and it's going to ask you in this first question, final V-bar offset, where do you want to get to relative to the target when you get there? So you just answer a few simple defining parameters of that sequence, and then it will calculate all those pieces needed to effect that V-bar hop maneuver. And then you simply stack these up to perform an RPO mission. And we're going to do a full demo on that coming up shortly. Let me just show you a few example RPO sequences expanded. Now, what's under the hood? These are all built in now. Astrogator sequences underneath the top sequence. So we're using built-in Astrogator capability to affect these types of proximity operation pieces. So under V-bar hop, there's a target sequence. And you have to start the maneuver. It's a radial maneuver. Then you propagate to the other side where you stop it, and then you've effected a V-bar hop. A V-bar hop is essentially, by the way, half of a natural motion circumnav. It takes half of a rev to complete. That's the definition of the V-bar hop. The hop and stop, you can see there's a hop maneuver, a propagate until you want to stop. Now the natural motion circumnav, this one on the right, is a bit more complicated because we need to join it at potentially any spot on the circumnav for whatever, for lighting reasons or whatever. I want to join it here at this time. So there's some extra complexity in defining it, and it takes up many more sequences. But again, all the user needs to understand is what's that top one and what are those input defining parameters. And when we do the demo, we're going to add a circumnav and take a look at that particular one. So the sequences that are ready now to use by our customers are a set of about 30 some odd sequences, different rendezvous and proxops parameters that you can push together now to form a complex mission. So here's an example mission, and you can see what it does. First step sets a reference vehicle to the target. Who is the reference for this phase coming up? So in other words, I'm going to set my initial state, but it's relative to whoever I told it in step 1. So step 2 says, oh, I'm going to sit on the V-bar relative to a target satellite, and I would have told it in step 1 who is the target satellite. Then I want to coast for 1 day, V-bar hop to minus 300 meters, coast for 12 hours, initiate an NMC and persist in it for 1.5 revs. Then I want to hop to a point on the radial direction, on the R bar, as it were, and then I want to perch there for several hours before I exit the scene. So this is all you have to need to be able to do using these sequences to build this, sequence. So that sequence ended up looking like this. We initially came in here. If you can see my cursor, you can come in here. We rendezvoused onto the V-bar. 1 kilometer to the west of the target. Then we V-bar hopped. Then we joined a complex natural motion circumnav for 1.5 revs. Then we hopped up to a perch point where we sat for 3 hours to inspect the target hopped up to the R bar, and where we inspected the target from that position on the R bar for 3 hours, and then we exited the scene. This is a list of, for example, all of the maneuvers that were required to do that entire mission. So a standard report coming out of Astrogator. And then a couple of classic plots, radial intrek, cross-track position, and velocity charts relative to the target. So those are pretty common ones to want to look at. Let's go ahead at this point and get into a demo.
And as a reminder to everybody on the webinar today, we will be taking questions at the end. So over in the GoToWebinar questions panel, if you have questions for Doug, type them in there and we'll be answering them after the demo portion of the webinar.
Thanks, Josh. Okay, so I've brought up Astrogator now, and this is that same scenario we were just seeing in the charts. Here I start with I give you 3 little building blocks. You first must set who is your reference, then what is your initial state relative to that reference, and then I just put in a coast to see what happens from there. So in this case, my reference was the reference was the target satellite, and I am RPO satellite. That's who this is under. You can see that I'm here. I am the RPO satellite. I set my initial state relative to him to be 0. 0 offsets in all directions, so in a sense, I am the target satellite. So you can see in the 3D graphics that the RPO satellite and the target satellite are one and the same at this point. Well, that's not a very interesting proxops. What we're going to want to do is, in this scenario, I have several satellites. I have one at 90 degrees west, a geosatellite. I have another geosatellite at 105 degrees west. I'm going to label the satellite at 90 west to be my chase satellite. He is going to become the RPO satellite. And we want to do a mission around the target satellite. So the first thing I'm going to have to do in set reference vehicle is, my reference vehicle is not the target. It's going to be chase. And I want my initial state to be 0 here. So I'm going to leave that alone. And I am going to be chase satellite now, not the target satellite. First, let me fix my typo. And then I'll rerun this, and you'll be able to see that the chase is no longer there. The RPO satellite is no longer there. He is down there. As you can see, he's part of the chase. He is sitting there on the chase satellite. So I've inherited the chase properties, and I'm going to effect a change. Now, I have another satellite called V-bar reference. This guy here, let's go ahead and put him on the V-bar at 1 kilometer from the target satellite. So I just found out what it takes to get there. My target satellite is the target, and I am V-bar reference. If I go ahead and show him on this on the 3D picture, and pull up my 3D graphics, you can see I now have a satellite sitting off to the west of my target satellite. What I want to do is rendezvous from the chase satellite to the V-bar reference at this point. So let's go ahead, and after this coast, I need another. This is how you get access to these sequences. Normally in Astrogator, if you're Astrogator users, you've seen these, insert these default segments. But there's a whole nother folder in this scenario that says I want to do a different sequence. So the first thing I'm going to add here is set reference vehicle. And I need to set it to V-bar reference now. Set reference vehicle. And now, instead of chase being who I'm relative to, I'm going to be relative to V-bar reference. Next, from here, we want to rendezvous. So I'm going to do a geo to geo rendezvous, only I brought the wrong one in. Let's delete that. Let's insert before a geo to geo rendezvous because I don't need the lead. So I'm going to drift at 3 degrees a day west from the current chase position. Just to save time here, we'll do all the calculations impulsively. And I am still the RPO satellite, which was the default name I used in these sequences. So now we're going to rendezvous onto the V-bar, and we're going to go from being the chase satellite to being the V-bar satellite now. And all I told it was I wish to drift circular at 3 degrees a day westward drift. Once I get there, let's go ahead and coast just to prove that we are staying there. And we're going to go ahead and coast for 1 day, which is the default in the coast segment. And you can see that when I added another coast, it incremented the name from coast to coast 1. And in this case, we just wish, my definition is 1 day, by duration, 86,400 seconds. So let's go ahead and run this. And let's see the rendezvous portion getting planned for us. And it's just going through the various sequences that it needs to do. In the rendezvous portion, it needs to actually start a drift rate, a circular drift rate towards the target. Then it needs to match its plane. Then it needs to drop down at the right time and become the V-bar offset satellite. And then we're just going to coast from there. So it finished. And you can see now, as I zoom out, there I was, the chase satellite back there, initiating this circular drift. And then at some point here, you can see that the planes were not matched by the squiggliness of that line right there. We matched the planes and came on in. And now, as I zoom in, you can see that I'm sitting on that equivalent of what was the V-bar reference. I've matched him completely. I'm going to go ahead and just uncheck him so that we can see that. But let's go ahead and take a look at some plots during this phase. So you can see this is a radial in-track cross-track difference between the target and that RPO satellite. You can see the drift phase here as the in-track gets closer and closer. And finally, it gets down in here, and we should be able to see it sitting for 1 day on the V-bar. So no radial or cross-track differences, just a 1 kilometer in-track difference, minus 1 kilometer, sitting to the west of the target. Let's see what type of maneuvers that took. So here is that maneuver summary report. It looks like it took about 19.26 meters per second to start and stop the 3 degree per day drift rate, and then the plane match was very small for a plane match. They were nearly matched before, just took 2.15 meters per second of that total 19. Let's go ahead and we'll just take, here it is a view just of the in-plane difference, but let's take a look here at the range difference. You can see again, it started quite a ways away, and then zooming in, we should be just 1,000 meters off the target when we get there as I zoom in. So there we are, sitting 1,000 meters. And just for perspective, the drift rates during that phase, we started out, we were the chase satellite. We had 0 degrees drifting. We were in a slot at 90 west. I initiated a 3 degree per day westward drift rate. At the right time, it came in and became on there. We can also look at what did the eccentricity do during that time. We flew circular during the drift phase, and these are just the home and transfer. For a half a rev there, you have a little higher eccentricity, but during the drift phase, we were drifting at near circular. So let's continue on with this demo. After we are now sitting off to the west, now we need to set the target satellite or the reference vehicle as our target now. So we'll come in, set reference vehicle, and the default is correct. We wish to set the reference now to target. Now we're going to V-bar hop towards our target. And again, I open up this folder with all these RPO sequences, and I'm going to choose V-bar hop. And it's asking me, where do I want the final offset? We're going to leave that alone, and we're going to set this to an impulsive calculation. It just saves us a little time than going through the finite calculations on top of the impulsive ones. So now we've hopped in. Let's go ahead and coast for another day at the end of that hop. So RPO, coast, just one day, 86,400 seconds with the definition set to duration. So now we are there. So let's go ahead and rerun this. And let's see what our mission looks like now. So it needs to just go through the whole set of sequences again, but it goes through very quickly because it already has the answer to everything we've done so far. Okay, so now it's already done, and now you can see at the end of that segment, we still have everything there. Remember, our whole mission from the rendezvous all the way in to the coast phase here. Then we hopped over, and now we coasted for one more day at the end of the hop. We can look at this in an RIC plot again, and here's what that looks like. The hop started at 1,000 meters to the west, ended at 300 meters to the west, and again, zeroing out the radial and the cross-track components. So that's what that looked like. We can look also at the additional maneuvers. Notice that the two maneuvers to affect the V-bar hop sequence, that they only take 1.2 centimeters per second each. So the bulk of an RPO's mission delta V is clearly in the rendezvous phase. Once you're in close, the maneuvers are much smaller in magnitude, and you can persist for quite some time with very little delta V in general. But we're not done yet. From here, after we finish that V-bar hop, we want to introduce that natural motion circumnav. So let's go ahead and insert a natural motion circumnav, NM circumnav. Now, a natural motion circumnav has a lot of degrees of freedom. First, there's the size parameter. You can either choose to specify the semi-minor or the semi-major axis. I chose to use the semi-minor. So you know that the semi-major is twice. It's the 2-to-1 ratio. So it's 300 meters in the in-track direction and 150 meters in the radial direction. The cross-track offsets, these allow you to specify, as it were, a relative plane of the natural motion circumnav. So you can have essentially a relative inclination and a relative RAN to the natural motion circumnav. This initial phase angle is where do you wish to join the natural motion circumnav. This is where you'd specify that in order to have the sun at the right place, for example. How long do you want to take to get from your current position to the start of the circumnav? I've simply said 10 minutes. The in-track offset is I don't have to center the satellite in the natural motion circumnav. It can be offset and not at the center of the ellipse. So I said offset at 150 meters in the in-track direction. The drifting parameter is what allows for you to build spiral flybys. But in this case, I don't want to spiral away from him. I want to persist in the same natural motion circumnav. So we are going to follow all these. We're going to set this to impulsive again, and that is going to get us to the start of the natural motion circumnav. But since this is passively stable, I'll need to add a coast segment at the end of this. And here's where I'm going to add coast for 1.5 revs. So coast, we're going to say, I want you to persist in the natural motion circumnav for 1.5 revs. Not 1 day. I want to go exactly 1.5 revs before I'm going to be ready to leave. But let's go ahead and see what the mission looks like now, as we added a natural motion circumnav and another coast phase to this mission plan that we're building. So this again is going through adding all of this, and now we'll get the new target stages for the natural motion circumnav, and it will place this right where we want it in hope, and we should have a natural motion circumnav that's a fairly complex circle around this target. So you can see it is not centered on the target. I offset it 150 meters, and it has a relative plane. It is not sitting in the in-track plane. You can see that this is what's called a safety ellipse, because if your target satellite should for some reason perform an in-track maneuver, you never cross that in-track axis with him. You're sitting here essentially in a different relative plane, and you won't have to worry. So it's called a safety ellipse because of that reason. So it went around here, it joined it here, so it moved from my current position, joined the circumnav, then it went around it for 1.5 revs, and at the end of this, we're over here on this side and ready to do the next mission sequence. So from here, let's go ahead and hop up to an inspection point. So we're going to use hop and stop. Let's go ahead and see what that looks like. So I want to hop to, on the R bar, 500 meters in the radial direction above the target. I'm going to take exactly 2 hours to get there, and we're going to make him impulsive as well. So now he's sitting there at the top, on top of the target, 500 meters, but then I wish to persist there and hold that non-natural point on the R bar for 3 hours. So we're going to do perch, and I have 2 formulations per perch. We're going to use the perch max error sequence. We're going to persist for 3 hours. We're going to have just a 5 meter. We're going to say you cannot deviate from that 500 meter offset more than 5 meters. So perform all the maneuvers you need to persist for 3 hours with just a 5 meter error maximum. All right. So let's again do this impulsive. And we should be able to run from here again. So now we've added a hop to an inspection point, and then we wish to persist at that inspection point and hold that position for 3 hours, and this will compute all the maneuvers required to hold it for 3 hours. As you know, anytime you're on the radial direction above the target, and with 0 relative velocity, if you do not perform these maneuvers, it will tend to go up and to the west, away from the target initially. And it will leave the scene naturally and safely. So it's computing the multiple maneuvers here, and they're going to be required probably somewhere, I don't know, about every 30, 38 minutes to keep that type of tolerance of error in that persisting at that unstable point. Okay, let's go look at what it looks like. All right, so here it is. So at the end of that circumnav, and after 1.5 revs, it went, we hopped to the stable point, and now we're persisting there. Let's go take a look at some of these plots just for kicks. Here we go, and I'm updating this picture. There was the V-bar hop right here. Now we go in, here was the circumnav, as that looks like. And now you can see at the very end the hop to this 500-meter radial and holding it. Let's take a quick look at the maneuvers required to do this. So you can see each of these perch maneuvers, it looks like about 38 minutes apart, but they're only 1.8 centimeters a second each. So since our rendezvous phase, all of these maneuvers are quite small maneuvers in order to get this prox mission to persist as we desire. Now finally we're ready to just leave the scene. So we're just going to add in a coast segment, and we're just going to coast for 1/2 of a rev. And then we're going to exit the scene with a special sequence called exit geo. Insert before RPO, and we have an exit geo. We're going to exit with -3 degree per day drift rate. Remember, that's the same drift rate we came in on. And we're going to leave on the same drift rate. And then once we start that circular drifting orbit, which naturally is above the geobelt if it's going to the west, and then we're just going to propagate it for 3 days to see what it looks like. So we'll just type in 3 days of duration. And now we have our entire mission planned by building up this set of sequences that we've built for Rendezvous and Proxops, and running through it one last time. This is what it's going to run through every sequence. It's going to be one continuous mission from being the chase initially, 15 degrees away in the geobelt in a stable 90-degree west orbit there, non-drifting. And we rendezvous onto 105 west, onto a V-bar of a satellite sitting at 105 west. Then we performed a series of steps in our proximity operation there, starting with a V-bar hop, a natural motion circumnav, a hop and a perch. Now we're going to let it drift for 12 hours, letting it go, stopping the perch essentially. So the perch gets stopped, and we let it drift naturally because it will. That's not a stable point at 500 meters on the R-bar. And then when we get 12 hours later, half a rev later, we're going to initiate a sequence that lets it drift naturally at 3 degrees a day to the west and leave the scene safely. So let's see what our mission looks like. Here it is. Notice after it left the perch point, that's not stable. I told you it would go up and to the west. At the end of 12 hours, we initiated a 2-burn sequence to start a drifting phase. Notice the height above the geobelt is the same as what it came in on, the 3 degrees per day, and we let it continue for 3 days. So let's take one last look at what our plots now look like. So in the radial in-track cross-track, you can see, I'll zoom back out, you can see here it drifted in. We performed in this phase the proximity ops portion of the mission, and then the exit the scene phase as we're leaving the scene. Let's go ahead and take one last look at the delta V required for this. Again, the departure took another 8.6 approximately meters per second because we had to initiate a 3 degree per day drift rate. So similar to the ingress, the egress takes the same amount of delta V. to exit the scene. So we used about 28.92 meters a second for this mission, but the actual proxops portion was less than a meter per second. So as I said, the expensive portion is the rendezvous and the exit the scene. So anyhow, that will conclude this demo. And where I want to go to next, then, we'll come back into these slides, and I think going to talk just a bit about what we've seen. The RPO sequences, they're ready for some initial testing, and we're happy to help our users get these. The RPO sequences, there's about 34 of them ready for use, and we can help you learn how to use these. There'd be like a separate 3-hour training that we could effect if users are interested. We're happy to do that. And please contact AGI support if you are. So at this point, I'll turn it back to Josh, and we can open this up for questions.
Thanks, Doug. Great job. That's some really powerful stuff in there. One thing I wanted to mention for the 3-hour training, if you are interested in something like that, and Doug and I had talked about that a little bit earlier, is go ahead and write that right in the questions panel. So if you have questions for today's webinar, type them in there, but also be like, hey, I'm interested. I would be interested in taking that 3-hour class. Just let us know right there, and it'll give us a gauge of whether and when we can put this together. And then to Doug's second point is, can I get a hold of that scenario? And as Doug, like you mentioned, it's yes, but we want to make sure that you know what you're doing with it. And so we ask you request the scenario through support@agi.com. And with that, I think we're ready to take some of your questions.